Hi, and welcome to the Introduction to Shapes of Molecules and VSEPR Theory. This is an introduction video to Unit 4, Part B. So in Part A of this unit, we learned how to draw Lewis dot structures from the chemical formulas. For example, if you're given something like CCl4 or COCl2, you'll be able to determine its Lewis dot structures. And so at this point, you've sort of seen and practiced quite a bit of drawing Lewis dot structures from the chemical formulas. Now, Lewis dot structures are useful because they show us a couple of things. First off, they show us which atoms are connected by bonds. For example, in the first structure, ClCl4, we notice that all 4 chlorine atoms are connected to the carbon, and nowhere in the structure are two chlorine atoms connected together. They also tell us the types of bonds. So if you look at the second structure, for example, we see that we have 2 carbon-chlorine single bonds and 1 carbon-oxygen double bond. So we can see the types of bonds that we have. And finally, we can also see in these structures we have some lone pairs. So they also show us where the lone pairs are arranged or how they're arranged in the structure. But Lewis dot structures, like most things in life, are not perfect, and so they have a couple of limitations. First off, they're limited because, as you can see from this molecular model, real molecules are not two-dimensional, but three-dimensional. And Lewis dot structures are two-dimensional. They're two-dimensional and they're flat. But in reality, molecules are going to be three-dimensional. They're not flat. And you may recall when you made your molecules using the model kits, your structures were three-dimensional. The other limitation is that you cannot tell the bond angles from the Lewis dot structure. So if you look at a Lewis dot structure, you can't look at it and say, oh, that's exactly what the bond angle is going to be. And we'll look more into that in a moment. So because Lewis dot structures have these limitations, we have to use what's known as VSEPR theory, or valence shell electron pair repulsion theory, to create VSEPR type structures. And they're used to sort of fill in these gaps about showing the three-dimensionalness of molecules and then being able to predict the bond angles. And so this is an example of what a VSEPR structure would look like. Okay, so we mentioned that one thing that VSEPR structures do is tell bond angles. So let's take a look at that for a moment. So first of all, what is a bond angle? A bond angle is an angle formed by 3 atoms connected together. And so let's look at a couple examples. Here in a water molecule, H2O, we have the bond angle that's drawn in here. And you can see that these 3 atoms are connected together, and the angle that forms between them is known as the bond angle. Here's another example with methane. We have these, if you take these 3 atoms here, these 2 hydrogens and this carbon, they're all connected together, and they would form a bond angle. So an angle is bond angle is formed between 3 atoms that are connected together. Now, as I mentioned before, Lewis dot structures will not tell you what the bond angle is. And if you take a look at this Lewis dot structure for methane, for example, if you look at it, you would think, oh, well, the angle formed between these 3 atoms, the 2 hydrogens and the carbon that are all connected together, you might think, oh, that looks like a right angle, so I would predict it to be 90 degrees. But it turns out methane does not have a 90-degree angle. If you look at the VSEPR structure, however, you get a better sense of the angle. So let's take a look at that. So here is the VSEPR structure of methane. And what you'll notice here is that this angle is slightly larger than a 90-degree angle. And so it turns out that the bond angle in methane is actually 109.5, which is slightly larger than a 90-degree angle. So you can more correctly see what the bond angle will be from the VSEPR structure as compared to the Lewis dot structure. Okay, so we're mentioning this VSEPR theory and VSEPR structure. So what is VSEPR theory? VSEPR stands for valence shell electron pair repulsion theory. And as we talked to you before, it's used to predict both the shape and the angles of a molecule. Well, let's break down what valence shell electron pair repulsion means. So let's start with the words valence shell electron pair. You may remember when drawing the Lewis dot structures that the bonds and the lone pairs actually come from the valence electrons or the outer shell electrons from the atoms. So both the bonds and lone pairs, they're all from valence electrons. And so when we say valence shell electron pair, that's exactly what we're talking about. We're talking about the electron pairs in both the bonds and lone pairs. Now let's look at the next keyword, which is repulsion. So what does repulsion mean? Well, remember, things that repel each other or are repulsed from one another, they want to be as far apart as possible. And that's super key here, because essentially what this theory tells us is that according to this theory, the shapes and the angles in a molecule is going to result from the fact that the bonds and lone pair want to be as far apart from each other as possible. Because remember, electrons have like charges; they're both negative, so they're going to repel each other. They want to be as far apart as possible, and so that's what's going to determine the shape and the angle. Now, of course, it's going to depend on the number of bonds and the number of lone pairs as well, but that's the key tenet of this theory. So what you can do is, if you know the number of bonds and lone pairs, which are kind of shown here in this chart, you can predict the electron domain geometry, and you can predict the shape. And this is something that you're going to do or be able to do by the end of this unit. Now, before you watch a video that kind of gives you a better preview into how VSEPR works, I want to talk to you about why we are learning this anyway. Why would we want to learn this? So it has to do with the fact that the structure determines function. And you may recall this very common example about which vehicle would you choose depending on the purpose. So for example, if you wanted to be in a race, you're most likely going to choose the sports car here because you can tell from the structure of the sports car that it's sleek and is aerodynamically favorable, so it's gonna be fast, and that will help you win the race. Whereas on the other hand, if you were trying to move out of your apartment, which vehicle you would choose, you probably want to go for the pickup truck because it's large, it has a truck bed in the back, and so you can sort of fit things in there. And so this idea of structure determining function is also something that we use in science all the time. And so by knowing the VSEPR theory, it helps you to get a better sense of the structure of a molecule, which can then therefore lead you to better understand the function or predict the function of a molecule. So that's why we learn VSEPR theory, just to get a better sense of the structure so we have a better understanding of the function. Okay, so what are your next steps? Your next step is, at this moment, you kind of learn some, or hopefully learn some new things in this video. So you're going to fill out the L column of your KWL, and I want you to emphasize the limitations of Lewis dot structures and the usefulness of VSEPR. Also, you might want to include what VSEPR means. After you've filled out the L column, then you're going to watch a second video on VSEPR, which gives you a better sense of how VSEPR actually works. And then you'll fill out the L column again. All right, so that's it for this video. Hope you found it helpful. Have a quality day.